there are not only single atom ions. There are things like CO3 with a 2 minus, or SO4 2 minus, or NO3 with a single minus. Phosphorus, well, if you have PO4 3 minus. So that's no longer, when we had phosphorus it was P3 minus, but you can also get an ion where there's extra oxygens attached to it. These are polyatomic anions. The idea is these are molecules. These are molecules that have a charge, where all the ions we were talking about earlier were lone atoms that had extra electrons or lost some. These are molecules where multiple atoms came together and are stuck to one another, but there's just a few extra electrons on them. There are, in fact, polyatomic cations. We'll talk about one. They are not nearly as common. Well, when you have a polyatomic anion, you just treat it like the charges. So we had some 2 minuses earlier. We still have some 2 minuses. If I have sodium pluses and CO3 2 minuses, I still need enough positives to counter my negatives. So if I'm trying to pair sodium ions with these, well, they're called carbonates, but we'll name them all in a second. With these CO3 2 minuses, it's a 2 to 1. How we write that is Na2. So we write our sodiums. There are 2 separate sodiums. This isn't some kind of weird 2 sodium molecule. This is the 2 independent sodiums. We're just saying there's 2 of them. And then you have CO3, which, well, that's the odd part. These sodiums represented 2 separate sodium ions, but the CO3 represents 1 intact molecule. So we'll talk about how we identify those parts, but this is how you'd write it. You'd have your sodiums and your carbon. And so we still have our cation, and we still have our anion, just as before. When it comes to polyatomics, the naming isn't as nice. The suffixes are ate and ite. There's a pair of them, depending on what you want, where your situation is. So, how do we know what ending we're going to use? Well, you don't. Not quite. Here's a short list. Let's say SO4 2 minus, SO3 2 minus, NO3 minus, NO2 minus, CO3 2 minus, HCO3 minus, PO4 3 minus, OH minus, CN minus, and NH4 plus. So a little more info on the page there. But those 10 are going to be the only 10 polyatomics you have to learn for this class. But you will have to learn them. Unfortunately, there's just nothing to do but to memorize them. So, how do we apply ate and ite? Well, when you have a polyatomic anion, so there's one exception over here, we'll talk about our cation a little bit later. But for all the rest of these anions, focus on the element that isn't oxygen. So you'll notice a lot of these are, say, sulfur plus some oxygens, or nitrogen plus some oxygens, or carbon plus some oxygens, or phosphorus plus some oxygens. This is pretty common. A lot of our polyatomic anions are oxygen derivatives. We have extra oxygens on them. When those are the cases, what you do is you take the same original start. So sulfur, when it was monoatomic anion, we said sulfide. Well, we're still going to have sulf, but instead of ide, because ide is monoatomic, we have 8 or ite. If you have more oxygens out of your possible numbers, so there's a sulfur with oxygens that has 4 oxygens, there's a sulfur with oxygens that has 3 oxygens. If those are your two possibilities, the one with more is 8. The one with less is ite. Now, you have to know what possible combinations there are ahead of time. And these are the 2 for sulfur. The next 2 are the 2 for nitrogen. So if I have a nitrogen, one with 3 oxygens and one with 2, well, nitrogen, you drop the ogen, it becomes nitr. So it becomes nitrate. And one of them becomes nitrite. And so again, of my 2 options, well, one of them had more oxygens and ends in 8. One of them had less and ends in ite. But you'll notice, if we compare sulfite and nitrate, they both have 3 oxygens, but we use a different ending. The suffix does not tell you how many oxygens. It only tells you one of them had more. And so you can only compare 8s and ites within the same other element, within the nitrogens, or within the sulfurs, or within carbons. And so while it's a little bit of help, in the end, really we have to just memorize these 10. 8 and ite tells you it's polyatomic, and that it's negative, but we have to remember which one is which. If we go down to our CO3 2-, this is, let's use same color. This is carbon 8. For whatever reason, we don't cut any part of carbon off, we just slap 8 on the end. There is no carbonite. If you lose one more oxygen, you just become CO2. You become carbon dioxide. That's not an anion. So if you only have one version, 8 is the default. Ite is only for when things have less. Way over here on the top left, HCO3-, well, our oxygens don't change. So this is still a form of carbonate, but putting one hydrogen on and getting rid of one of your 2 negatives makes this a bicarbonate. In fact, you can make bisulfate if you have HSO4 with a single minus. The idea is if you have the ability to put 2 hydrogens onto an anion, and you only put 1, you are on the second step. So you are the second carbonate species, the bicarbonate, like a bicycle, and that is where that comes from. We will talk about, it's the only one we're going to make you memorize for this one, but bicarbonate is very important for things like the respiratory system. There's a ton of it in your bloodstream and in your cells. It's a very common ion in the body, and so it will come up in a lot of reactions and discussions. So it's one of the ones we have to remember. So next one down, phosphorus. Well, when it was monoatomic, it became phosphide, but now it has oxygen, so it is phosphate. And so the last ones here, unfortunately, don't quite follow our 8 and 8 rules. They were named very early on. They didn't have the naming convention yet, and so they still have their old names. OH- is hydroxide. Which, if we look at the name, oxide looks like O2-, and the hydro was a hydrogen on it. So basically the name was written as a monoatomic oxide that had a hydrogen attached, which is kind of what it looks like. It looks like an O2- with an H+. but nowadays recognize that that's polyatomic. At the time, it was named separately. And so it bears the old name hydroxide. Down to our next one, Cn minus is cyanide. This has the IDE, and it was just misnamed. What we knew is that if you mixed it with iron, you got this very deep blue cyan color. It's actually where Prussian blue or midnight blue, if you have Crayola crayons, comes from. The cyanide binds to the iron, and it makes this intense, beautiful color. And so it was actually named because it made the color. They didn't know it was a polyatomic anion at the time. They didn't know what it was. They just knew that it did this. And so cyanide bears its old name from the dye that it helped create back in the day. And our last one is actually our only polyatomic cation. It's not that there aren't others in the universe, but it's actually really hard to make polyatomic cations. They are substantially more rare than the anion. And so this ends in -ium. If you have NH3, you are ammonia. Ia goes away, and you become ammonium. And so the ammonium cation is our one polyatomic anion, or polyatomic cation that we need to know. And so this list is the 10 polyatomics that will come up on any kind of test or anything like that. And you really sort of just have to memorize them. I would make flashcards and whatnot to practice them, but these 10 will be required. I won't put any more in. There are a few others we might mention from time to time, but these are the only ones that will come up on test questions and the like. How we use them is exactly the same, though. If I want to talk about sodium sulfate, I will just name sodium and I will name sulfate. And a sulfate is an SO4 2-. So we can see that one up here. So it has 2 negatives, and my sodiums have 1 positive, so I need 2 sodiums for every sulfate. If I want ammonium, let's say ammonium chloride. Well, ammonium is a +1, chloride is a -1, so it is NH4Cl. If I gave you MgCO3, well, that is a magnesium, and if we look, that's a carbonate. The charge are left off in the formula, but if we look up above, CO3 is a carbonate. So this is a magnesium carbonate. And so we pair together polyatomics just like we pair together the monoatomics. Cation first, anion second. The important part is when you see something like sodium nitrate. Here we go. I have sodium nitrate. When I look at this, I see 1 sodium with a plus and 1 NO3 with a minus. This is the correct way to think of it. It is a sodium and it is a nitrate, so they are sodium nitrates. What we have to be careful of, and what we don't want to do, is think of this as a sodium plus an N3 minus and 3 O2 minuses. If we do that, this looks like 6, 7, 8, 9 negatives and 1 positive. this would not give us a neutral formula, and we can see from our molecule there's no charge. We were neutral. So this cannot be what is happening. So when you see what is clearly a cation followed by something else, could it be multiple different monoatomics? Possibly. But if you tried that, would the charges work? Clearly it doesn't here. I have way more negatives than positives. If that's the case, I have to go back and think to myself, well, what if this was polyatomic? Do I know any NO3 polyatomics? Let me go back up and say, oh yeah. Yeah, I do. The nitrate. It comes with a 1 minus. So I go back and fill that in and say, does that make sense? Hey, yes. +1, -1. That balances my charges. This must be telling me I have a nitrate, not I have a nitride and 3 separate oxides. And so we have to do a little bit of checking when we look at it. But that is the basis of naming ionic compounds, basic ionic components. So if you have any questions, hopefully we're in class, but if we don't have that, go ahead and email me. But hopefully you guys can give a little practice to some compounds and feel comfortable with me.